Morning. Okay, so let's go over the notes for 5.4. It'll only take half the period, and we'll use the second half to continue reviewing in your test packet. Okay. So yesterday we learned about how we can go backwards from the natural log rule. Natural log rule is u prime over u, and also we talked about how we have a specific rule where power rule fails. But if I'm working with x 1 over x, I got to make it x to the -1, and power rule is not going to work. So we have a rule, natural log integral rule. Okay, so that was yesterday. Yesterday we learned that the antiderivative of 1 over u du, if it's in that form, it gives us natural log absolute value of u plus c. Okay, but it only works if it's u to the first power in the denominator. If your variable in the denominator is any other power, you got to bring it up to the numerator, change the exponent, and go through power rule. Okay, so today we're talking about integral exponential rule for base e. Okay. First semester, we learned that the derivative for e to the u is e to the u times u prime. So it stands to reason that if I want to work backwards, the antiderivative of e to the u will bring us back to e to the u as well. So these many consider the easiest derivative and integral rules because they're basically just it themselves, right? Just have to keep track of the u value a little bit, but essentially, e to the u is just e to the u, forwards and backwards. Okay. So if we look at example 1, find integral of e to the 3x plus 1 dx. If your rule doesn't look exactly like the one that you want to apply, then you want to go through U-Substitution so you can keep track of potential coefficients that needs to be worked out. So if we're trying to match, we see a similarity between the rule and the problem that we want to use. What could be our u value to make things match? Yeah, let's let that entire exponent be the u value and see if we can get it to match with the rule and if there's any leftover coefficients that we're able to keep track of that as well. Okay. Okay, so du dx, we have to find the derivative. Okay, so 3x becomes 3, and 1 goes to 0. Okay, so cross multiply here, trying to solve for dx. Okay, dx equals du over 3. Make our substitutions. No x's remain, that's good. But there is a leftover what? Yeah, so you got to push that 1/3 out in front. Okay, so now if you look, perfect match with the rule that you want to use. So therefore it becomes 1/3 e to the u plus c. Okay, replace the u back in terms of x. Okay, any questions? All right, take a look at number 2. Integral of cosine of x e to the sine of x. Okay, so I want to keep reminding you that even if you see a couple of rules that look like they can be separated and you can handle them one at a time, we can't improvise with integral rules, right? It's got to match exactly like it. We can't separate rules unless there's an addition sign in between. So this is just one extended problem that is too much for any one rule to handle. So we have to go through U-Substitution. Right, so what could be a u value that will allow this problem to maybe match one of the rules that's available to us. Yeah, let's target that exponent, right? And we're hoping that this sine will take care of that cosine. And if we think about our derivative rules, those should pair up nicely. So okay, derivative. What's the derivative of sine? Cosine. Okay, cross multiplying. Okay, substitute. Leave the cosine there for now. Okay, what do you see? Cosine goes away. X's goes away. That's the first thing. Coefficients, nothing to keep track of. And then we got to make sure that our remaining problem looks exactly like the rule that we want to use. It does. So we can move forward. Okay. E to the u is just e to the u plus c. And finally, we have our answer, but bring back our original variable. All right, number 3, integral of e to the x over 2 plus e to the x. We can't jump in and say, oh, there's an e to the x, I'll take the antiderivative there. There's an e to the x in the denominator, I'll take the antiderivative there. This is connected by division. This is all one problem here. So we don't have a rule that looks exactly like this, so we have to turn it into a rule that we can use. So we got to simplify this process, simplify this problem. Okay, what could be your u value that could work here? Well, if we bring that 2 plus e to the x, make it raised to a -1, we're still stuck not being able to expand. We still got to go and find our u value. Okay, so what could be our u value? The denominator. Okay, and now we're going to be targeting potentially a different rule here. So the different rule here is we have this rule from yesterday. So it looks like this will be a good fit for yesterday's rule, right? If we let that u value be the denominator, we're hoping that the e to the x just goes away on its own, and if we can kind of imagine that this could be a potential fit. Okay, so let's see if this works out. Okay. U equals 2 plus e to the x. Okay, remember the derivative for e to the u is just e to the u times u prime. Okay, so du dx. 2 goes to 0. Okay, what's the derivative of e to the x? E to the x, yeah, times 1, which you can leave it there, but you know, just a reminder that yes, you're always looking for that exponent's derivative, chain rule, but in this case, nothing's going to come out of that, so solve for dx. Make your substitution, and let's see if we can make things work out to make it match a rule. Okay. Yeah, e to the x cancel, and it needs to look exactly like the rule that we want to use. We can't improvise. We can't have any changes. I mean, we can have coefficients out in front, but after that, it needs to match to the letter, and it does. Okay, so now we can apply our antiderivative rule, natural log absolute value of u plus c. We have our antiderivative, and then bring your original variable back. Okay, questions? Okay, back page. Okay, look at example 4. Obviously, we don't have a rule that can handle such a messy problem. Okay, and we can't separate e to the x from cosine e to the x. They're being multiplied. So we got to go through U-substitution. But we need to kind of strategically choose the u value so that the x's goes away and we're left with something that has a matching rule. So any guesses as to what our u value could be here? Yeah, inside the parentheses. There are two e to the x's, but we want to target this inside parentheses. We want to leave this e to the x alone for the derivative to match and cancel out. So if you can kind of look ahead to what this problem could be, maybe we can target this rule here. Right? We have a rule for cosine u du, and it looks like we're able to kind of work towards that end, right? So the it is a bit of trial and error with U-substitution, but the earlier that you can kind of visualize what the problem could look like at the end, the easier it is to kind of potentially pick out the u value and kind of look ahead to see what will work or what won't work. Okay. Derivative of e to the x is e to the x, cross multiply. Okay, did the e to the x go away? Yes. Okay, you guys remember the rule for cosine, for antiderivative of cosine? Is regular sine, right? I know that's the tendency for us, but if you remember, the derivative for sine is cosine. Right, and because the derivative of sine is cosine, the antiderivative of cosine is going to be a positive sign, right? Antiderivative is working backwards. I know it's easy to say it's negative sign because we're used to seeing that for our derivative rule. For antiderivative, you're starting on the right side of your derivative rule, making your way up to the original function. Okay, so just going to be positive sign. Okay, replace u back in terms of x. Okay, take a look at 5. Too complex for one rule to handle. We can't separate the numerator and denominator and treat them like separate problems. They're connected. So we have to go through U-substitution in the hopes that it will turn into one of our known rules. Okay, any guesses as to what the u value could be there? Denominator. Okay, try that. See how far you can get. Okay, what's du dx? Good, e to the u times u prime. We got to remember about that chain rule there. That exponent is going to have to remain a part of it. Okay, cross multiply. Okay, we make our substitutions. What goes away and what remains? E to 2x goes away. That's the important part. Yeah. What in front? Okay, as what? Uh-huh. But is it just 2 or something else? It's in the denominator, right? So 1/2. Okay, 1/2. Okay, now that everything is cleaned up, you look, cover that 1/2 up. It looks exactly like our integral rule from yesterday, so we can move forward. Okay, and then replace the u back in terms of x. U is only temporary. There's your antiderivative. Okay, take a look at number 6. Too messy for one rule to handle. We have to go to U-Substitution. What could be our U value? Denominator again. It looks like it's not going to do a good job of matching the top, but we'll be able to just work with the numerator a little bit later to at least get some common factor. Let's start there. Yeah, start with the denominator, and it's going to feel similar to 5, at least in the beginning. Okay, what's the derivative? Good. There's going to be that leftover -1 from that second e to the negative x. We can pull that out as a negative. Okay, cross multiply. Okay, let's substitute and see what we can do with that numerator mess. Almost. We see there's definitely some similarities, right? But it's not quite perfect. Is there anything we can do so that we can get a perfect match, at least portions of perfect matches to go? Yeah, what if we take out a GCF of 2? Let's see if that will help. All right, now we have some common factors, right? We can treat this like its own parentheses. That's its own parentheses. There's no addition or subtraction that's conflicting it. We can match and pair these common factors and make them reduce. Okay, looks pretty much like our 1/u rule. There's a coefficient of 2. Once that 2 comes out, you should be convinced that you can apply the integral rule.
So you can't just cancel out the numerator earlier, just leave the 2.
I mean, if you are understanding that the factor of 2 is coming out, but we really can't just take these out technically we're not supposed to cancel across addition and subtraction, right?
But you can skip that step if you.
But you can skip the step if you understand that it's really a factor of 2 and you're reducing the remaining portion. Yeah. Okay, any questions? Okay, let's go to our test review. Let's go to page 8. Did we finish page 7?
Yeah.
We did, okay, all right, so page 8. It's another particle motion, or rather a table of values, Riemann-Sums problem. Okay, page 8. Okay, so it says Joanna jogs along a straight path for t-values between 0 and 40 minutes. Joanna's velocity is given by a differentiable function v. Select the values of v of t, where t is measured in minutes and v of t is measured in meters per minute, are given in the table above. So let's just observe what this table gives us. So we know that at 0 minutes, she hasn't started running yet. 12 minutes in, she's running at 240 minutes, 200 meters per minute. 20 minutes in, she's picked up her speed, 240 meters per minute. 24 minutes, negative 220 meters per minute. What's going on here? You change direction, right? So she's jogging along the straight path in the positive direction, but then she's going to backtrack and she's going to turn back where she came from, and she's going to make, go in the opposite direction. But then at some point in time, she's going to turn back around and she's going to start going forward again. Okay. We don't know exactly where, but we do know that somewhere she definitely changes direction at least once, right? Okay, so there's the picture of just a general idea as to her movement here. Okay, so part A says interpret the meaning of v prime of 20 and indicate the units of measure. So v of t is meters per minute, so v prime is going to be what? Okay, it's going to be acceleration, right? But I also want us to be able to get into the habit of knowing how to represent this, basically a rate of a rate, but be able to represent it in a way that that's more suitable. Okay, so we can say that this is telling us, v prime of 20 is telling us, okay, is the rate that her velocity is changing. Okay, for this particular problem, you could just say acceleration, but I want to kind of give a general idea that if you want to say a rate of a rate, this is a way to say it. You can say the rate that this rate is changing. Okay. The rate that her velocity is changing at t equals 20 minutes. Okay. And the units is, what's the unit of measure? Right, meters per minute, which is meters per minute squared. Anytime a derivative or integral is involved, you want your units to change, right? Either if it's derivative, you're going to keep adding more and more denominator units. But if it's antiderivative, you're stripping away that denominator unit. Okay. I want to make the connection with yesterday when we're going through page 7. Look at how this is not acceleration velocity position, but we can still go through that same wording, right? We know that C of t is ounces per minute, so C prime is how fast the rate of water added is changing, right? You're including those words to indicate that you're talking about the rate of a rate, but you're saying it in a way that is that's clear, right? And also the way that College Board AP exam for response is going to be able to accept. Okay, so just want to kind of point that out. Okay, part B, approximate the value of v prime of 18 and indicate the units of measure. So v prime of 18 is the derivative of velocity. We don't have a function to find the derivative, so the best thing we can do if we're given a table of values is just to find the what? Rate of change, right? What's another word for rate of change? Slope. Okay, so derivative, rate of change, slope, right? Those are all connected. Sometimes you can use if you have a function, you can find the exact rate of change, but here the best you can do is approximate it, because we'll just pick values that are closest to our source, right? We don't have anything involving 18, but we have 12 and 20, and those are the closest order pairs to 18 minutes. So acceleration is just change in velocity over change in time. So we do change in velocity over the change in time. Okay, we get 40 over 8, which is 5, and our units of measure again is what? Yeah, meters per minute squared. Okay, part C, interpret the meaning of the definite integral from 20 to 40 of v of t and indicate the units of measure. So integral of 20 to 40, as a reminder, we know that antiderivative velocity will bring us up to position, okay, and our units of measure will change from meters per second to be what? Just meters, right? Anytime you take an integral of a function, that units of measure is going to change, right? In this case, we're going to strip away that denominator unit. So as also think about, this is basically first theorem, right? First theorem says, if I take the integral of a function, f of x, that's going to turn into its antiderivative, indicated by uppercase f, and then we subtract our upper bound minus the lower bound. Okay, same thing here. Integral from 20 to 40 of v of t. We know v of t, antiderivative, will transform into x of t, position. And then once you get your position function, then you can just subtract upper bound minus lower bound. Right, right. So this is I think this will help. X of 40 minus x of 20. What does this mean? Yes. Okay, this is the change in distance between 20 and 40 minutes. Right? Let's say 40 minutes, she's at she's 2 miles or 600 meters into the run, and then 20 minutes, she's 400 meters into the run. And so if you subtract those two, you can figure out the change in distance. In other words, displacements. Okay. So in other words, our displacement, which is the net gain between 20 and 40 minutes. We don't care exactly the fact that she's backtracking. We just want to know how much progress does she make between 20 and 40 minutes. It's just comparing that distance between the 20 and 40 minute mark. We don't care about her movement anytime in between. Okay, and the units is going to be meters. So part D, we're going to actually get a number out of this process, because we're going to approximate the value using two trapezoids. Okay. Make sure you memorize, just like how you did on the quiz, area of a trapezoid. What's the area of a trapezoid? 1/2 width, and then height 1 plus. Yeah, make sure that you're adding. I saw some students on the quiz subtracting the heights. Okay, we're going to be adding the heights. Okay, two trapezoids between 20 and 40. So we look at our table, and we want to separate our interval into two subintervals. Now we can just both will span across two order pairs. We do subtract the time to get the width. Okay. So the width for my first trapezoid is going to be 4. Width of my second trapezoid will be 16. Okay, 1/2 width times height 1 plus height 2. That's my first trapezoid. Second trapezoid, 1/2 width times height 1 plus height 2. Okay, all this cleans up to be 40 minus 560. Units is meters. Okay, C and D are talking about the same situation. This is describing it, and part D is finding it. So can you put into words, what does this mean? What does that negative 520 meters mean for in Joanna's case? Yeah, so she's 520 meters to the left of where she started at 20 minutes. So between 20 and 40 minutes, doesn't matter that she's backtracking forwards and backwards. If you compare the distance between 20 minutes and 40 minutes, she's going to be 520 meters in the opposite direction of where she started at 20 minutes. Okay, part E, approximate Joanna's average velocity between 20 and 40 minutes using the results from part D. Okay, so average velocity is average value theorem. Okay, A and B is 20 and 40. F of x is your V of t. Okay, we can replace this piece with part D, right? We found an approximation of this using part D. Now, I want to point something out here. You see how the integral is going to take that velocity, which is meters per minute, into just meters? But then you're turning around and you're dividing by 20. So you're dividing by time, so you're back to where you started. So this is going to give us a unit that is meters per minute. So I just want to point that out here. It's kind of strange that, oh, average velocity, but I'm taking the integral of velocity. So how am I getting velocity? It's because I'm dividing by 20. And so I'm taking my position, dividing by time, I'm back to an average or units in terms of velocity. Okay, so this gives me negative 26 meters per minute. So this average velocity basically tells us that between 20 and 40 minutes, she's going to average about 26 meters per minute in the opposite direction. Okay. All right, let's go to page 9 and let's do a particle motion problem just to kind of talk about some of the features of one. Okay, particle moves horizontally, so that its velocity is given by this function above. So this is the velocity function. Anything above is positive velocity. Anything below is negative velocity. Anything on the x-axis is a velocity 0. This is differential functions, a smooth curve. The velocity is 0 at 1, 3, 7, and 9. And the graph has horizontal tangents at 2, 5, and 8. So this just tells us that there's a slope 0 at 2, 5, and 8. And this is also going to help us with our acceleration sine line when we're essentially looking for points of inflection. Okay. All right. The areas of the regions bounded are 2, 3, and 6. So these are the areas within those shaded regions here. So, but then in terms of displacement, we know that this means below means negative, right? So we know that in that region, displacement is going to be -2. Next, between 3 and 7 is a +3, and then 6, -6. So just to kind of visualize what's happening, this particle is going to move 2 units to the left over the course of 2 seconds, stops, turns around, moves forward 3 units. At 7 seconds, will stop, turn around, move 6 units, and then stop at 9. Okay, so just kind of visualize that process. Okay, and we're given that at time t equals 1, he's starting at location 2. Okay. All right, so it says part A, create sine lines for v of t and a of t. Okay, I'm extending from 1 to 9. My critical points are 3 and 7. Okay, so negative velocity, positive velocity, negative velocity. Okay, acceleration. We're also extending from 1 to 9, but now we're looking at the slopes and the peaks and valleys. Right? Acceleration is 0 at 2, 5, and 8. Right? That's what they tell us. Horizontal tangents at 2, 5, and 8. In terms of positive and negative acceleration, we look at the slope. Negative slope of velocity translates to a negative acceleration. Positive acceleration, negative acceleration, positive acceleration. Part B, on what interval is the velocity negative? Velocity is negative in these 2 intervals. The because statement is because v of t is less than 0. So that's, yeah. What interval is acceleration positive? Acceleration positive, we mark 2 to 5, 8 and 9. Because v of t is increasing. All right, positive slope of velocity function is going to translate to positive acceleration. Yeah, or we can say a of t is greater than 0. Yeah, question?
For the acceleration, how do you figure out like the positive values?
Right, if you're looking at the velocity graph, then your acceleration is based off the slope of your acceleration of your velocity graph. So from 1 to 2, negative velocity, negative acceleration because it's negative slope. And then from 2 to 5, positive acceleration because we have positive slope. It's like concavity. It's like concavity, finding concavity based off of your derivative graph. You look at the slope. Okay, part D, on interval from 5 to 7, is the speed of the particle increasing or decreasing. So how do we determine speed? Or speed increasing or decreasing? Okay, same signs, right? Look at 5 and 7. I lined the 2 sine lines up here. So between 5 and 7, positive velocity versus negative acceleration. These are opposite signs. Speed is decreasing. Interval from 7 to 8. Is speed increasing or decreasing there? Increasing, signs are the same. Okay, part F, find the position of the particle. So to find the position, we have a starting location. So we have to go through this formula here. Anytime I'm looking for a final position, it's going to be my initial position plus my displacement. So if I want to find the location at 3, I need to have a starting location, and the starting location I have from what's given to me. I know that at x of 1, I'm going to start off at location 2. So I know that's given to me, and then I need to figure out how much progress do I make between those two time intervals. So x of 1 is 2, and then the different interval from 1 to 3, that's just the fact that I'm going backwards 2 units. So that's 0. So that means at 1 second, he's at location 2, but then between 1 and 3 seconds, he's going to go backwards 2 units. So if he's going backwards 2 units, he's going to end up at location 0. Okay, to find x of 7, I start at my given location, and then I want to know how much progress do I make between those two time intervals. X of 1 is 2, and then between 1 and 7, go backwards 2 units, forwards 3 units, so -2 plus 3 is 1. So overall, he's going to make a forward progress of 1 unit, so after 7 seconds, he's going to be in location 3. Okay, I'm bleeding into the space here, but x of 9 would be, again, use your starting location and then build off of that. Okay, so between 1 and 9, so we'll go backwards 2 units, forward 3 units, backwards 6 units. So that's going to be -5.
Why is the 7 not 1?
1 to 7, it is 1, but then he's starting at position 2. So if he moves forward 1 unit, he's going to end up at position 3. So if I'm looking for my final position, it's going to be my starting position plus how much progress I made between those two time intervals. So it tells us that x of 1 is equal to 2. So you're starting at location 2, and then you're moving forwards and backwards based off of these numbers. Okay. Right, you add the 2 to -5 to get -3. Okay, let me skip. Oh, for G, it says state the absolute extrema. So absolute extrema just means EVT, right? EVT means find the positions at 1, 3, 7, and 9, and then just compare their y values to see which one is the highest value and which one is the lowest value. So x of 1 is 2, x of 3 is 0, x of 7 is 3, x of 9 is -3. So your absolute max is going to be 3, and your absolute min is going to be -3. Okay, part H, find total distance. Remember, total distance is just the definite interval of your absolute value of v of t. So total distance traveled, you just look at the areas and you just add up, treat all of them as positive values. So 2 plus 3 plus 6 is 11. Displacement just means how much progress did he make between 1 and 9. We don't care about the starting position. We just care about the integral from 3 to 9 of v of t. And here we do keep track of the positive and negative signs. So from 3 to 7 is positive 3. From 7 to 9 is negative 6. So negative 3. Okay, you won't be asked to sketch a graph on the test. Okay, so tonight, when you study for your test, I suggest that you try to go through the morning review. I'll do it tomorrow as well, but you'll see a problem like this, particle motion problem. Okay, a problem involving a derivative graph and definite integral and EVT and all that, and then a table of values. Right, so your key is attached. Work through that. That'll be a good way to study. Tomorrow morning, I will be available to go over these problems again. I have videos of these from previous years, so if you look on my website, Morning Review, I have a video going through each of the problems. So hopefully that'll be a good way for you to prepare.